Welcome to the fourth lecture video in our Class 17 series of lecture videos. Recall from lecture video 3, the reagent that reduces carbonyls that we talked about, sodium borohydride, so NaBH4. Here we've got it drawn out with a nice tetrahedral borate and our sodium countercation. And so, of course, the hydrogens really own the electrons in the hydrogen-boron bonds. And so they're going to use them to form a bond to our carbon. So here's our sodium borohydride attacking a carbonyl carbon, pushing a pair of electrons up onto our more electronegative oxygen, which then is associated with sodium. We typically do these reactions of sodium borohydride in methanol. So if we create a little bit of this alkoxide, Le Chatelier helps us deprotonate methanol, and we create a sodium methoxide and our alcohol. And then that methoxide goes and it attacks the empty p orbital on our BH3, and then we get methoxy sodium borohydride. So for a reduction like this and a reaction run in methanol, the process can be repeated. Our sodium methoxy borohydride can go ahead and add another hydride to another equivalent of some sort of carbonyl and generate another alkoxide and methoxyborane, and that alkoxide can deprotonate another molecule of methanol. We have plenty if it's a solvent, and then the sodium methoxide that's generated can go and form this dimethoxy sodium borohydride. So in theory, one could use a 4:1 molar ratio of ketone to sodium borohydride. Typically, however, an excess of sodium borohydride is used. And quite an exciting reaction, but there could actually be even more exciting reductions. So how about another reducing agent? And well, right under the periodic table, under boron is this interesting metalloid called aluminum. And so if you can have sodium borohydride, believe it or not, you can have something called lithium aluminum hydride, or we abbreviate that often as LAH. Sometimes you'll see it written as LiAlH4. In terms of electronegativities, well, boron's got 2.0, aluminum 1.6, and hydrogen 2.2. So you can conclude that lithium aluminum hydride is a stronger reducing agent than sodium borohydride. Why? Because there's a greater difference in electronegativity between the hydrogen and the aluminum than between the hydrogen and the boron. So hydrogen is even more tuned to be hydride and negative in lithium aluminum hydride. So it's a very powerful reducing agent, as one of my former students remarked. LAH, when it absolutely positively has to be reduced. So LAH cannot be used in the presence of an alcohol or any protic solvent. And why is that? Because it will react very quickly with the acidic or most acidic proton on our alcohol. If it's methanol, for example, we would get the lithium methoxy aluminum hydride. We'd generate hydrogen gas. This would happen very quickly and release a lot of heat, and that could be explosive. Two separate steps are preferred in these reactions. One step in which we treat our carbonyl compound with LAH in presumably some organic solvent that is water-free or anhydrous, and then very slowly after that reaction is done, we will quench it with some acid. Again, we probably use a little bit of excess LAH, so we're very careful as we go to add the acid once that reaction is finished, because we don't want to blow up or lose any fingers. So these reagents can also be used to incorporate deuterium. If you can have sodium borohydride, you could have sodium borodeuteride. You could have deuterated forms of methanol. So if you have both the sodium borodeuteride and deuterated form of methanol, you'll add 2 deuterium atoms. If you use sodium borodeuteride, but you use methanol, where you have 1H as your most common isotope of hydrogen, then the deuterium goes to the carbon, and of course, the oxygen gets the proton from the methanol, so it is a 1H proton. Similarly, you can do the same sort of thing with lithium aluminum deuteride, and apparently THF is a good solvent for this reaction. But wait, a carbonyl group has two faces. Can the hydride add to both? And that's an interesting question. Here we've got, a hydride could add to the top face or the back face. If the R groups are the same, it really doesn't matter, does it? Because your resulting product alcohol is going to be achiral. It doesn't matter unless the R groups are different. So say you have an R and an R prime, then you will get, a mixture of isomers, stereoisomers, and it's not necessarily 1-to-1. If they're enantiomers, yes, they would be 1-to-1, but if they are diastereomers, it may be a different ratio. So I think that concludes this video. We'll see you in the next.